Hey everyone, in this lesson I'm going to talk to you guys about the heme synthesis pathway, and I'm going to go through each step of the pathway, including going through each of the intermediates of the pathway, and I'm also going to look at particular enzymes in the pathway and how they're regulated, and I'm also going to tell you guys about the importance of heme within our body. So what is heme? Well, heme is a prosthetic group, so it's a moiety that is bound to a protein. And heme is actually a protoporphyrin 9 with an iron moiety. And what that actually means is that protoporphyrin 9 has 4 chiral rings, and I'll get into this a bit more, the structure of it and how it's produced a little later. So it has 4 chiral rings, and it has a iron moiety within the center of it, and you can see here in this heme molecule the center iron within the middle of it. So why do we need heme? Well, heme is required for hemoglobin synthesis, and as you already know, hemoglobin is a protein involved in oxygen transport within the red blood cells. And don't forget the related protein myoglobin as well, which only has 1 heme, and hemoglobin actually has 4 heme groups. And myoglobin is also important in oxygen transport. But nevertheless, when heme is used to produce hemoglobin, we actually call that the erythropoietic system. And this heme is actually produced in the long bones in our body. And this is actually where about 85% of the heme is produced, and it's actually produced for hemoglobin that is actually used in red blood cell and red blood cell production. So another requirement for heme is actually cytochrome synthesis. Now, cytochrome, you may have heard the cytochrome P450 system within the liver. Now that is the major detoxification pathway in the liver, and cytochromes are critically important in that detoxification system. Now, they're very important in hydroxylation reactions to detoxify particular drugs and compounds, and when heme is actually produced for cytochrome synthesis, we call that the hepatic system. And again, as I mentioned before, this hepatic production of heme is critically important for cytochrome P450 system within the liver. So how does heme production start? Well, it actually starts with the amino acid glycine and succinyl-CoA. And these 2 components are actually used by an enzyme known as ALA synthase, or aminolevulinic acid synthase. And this process actually occurs within the mitochondria to produce aminolevulinic acid. Now, this step in the heme synthesis pathway is the first step, but is actually the rate limiting step of the heme synthesis pathway. Now, within the hepatic system, hemin, which is a byproduct of heme, actually negatively inhibits ALA synthase, while reduced hepatic heme actually upregulates ALA synthase. So you can actually have reduced hepatic heme if you overutilize that cytochrome P450 system by, say, for instance, ingesting too much of some drug or some toxic compound. The cytochrome P450 system become overutilized and would actually require more heme production. And that is why a reduced hepatic heme would actually upregulate this enzyme to compensate. Now, in the erythropoietic system, iron and erythropoietin are actually the activators or upregulators of this enzyme. So once we have produced aminolevulinic acid, it actually takes 2 of them to actually go on to the next step. And the next step involves ALA dehydrase, which actually occurs in the cytosol. And this produces something known as porphobilinogen. And this enzyme actually requires zinc. And because it requires a metal, it can actually be inhibited by lead. So we all have heard that lead can cause anemia, and this is why lead actually can inhibit this enzyme, or inhibit ALA dehydrase. So once we have porphobilinogen, it actually takes 4 porphobilinogens to move on to the next step. And once you have 4 of these, the enzyme uroporphyrinogen 1 synthase will actually take these 4 porphobilinogens and in the cytosol, this is all happening in the cytosol, will release 4 ammonia and will actually produce uroporphyrinogen 1. Now, uroporphyrinogen 1 will actually be processed by uroporphyrinogen 3 co-synthase, also in the cytosol, into uroporphyrinogen 3. Uroporphyrinogen 3 will then undergo a reaction with uroporphyrinogen decarboxylase to produce coproporphyrinogen 3. So I know, guys, this is a lot of big words, but we'll get through it. So coproporphyrinogen 3 is produced from uroporphyrinogen 3 by the enzyme uroporphyrinogen decarboxylase. Now, coproporphyrinogen 3 will actually undergo another step via the enzyme coproporphyrinogen oxidase into protoporphyrinogen 9. So we're getting close there. You can see as we're moving on, this structure is becoming more and more like heme. So protoporphyrinogen 9 is produced, and then we'll actually go through a protoporphyrinogen oxidase to produce protoporphyrin 9. So this is we're pretty much there, but we're missing one thing, and that is the iron. And the iron will actually come from the last step via the enzyme ferrochelatase. And this actually happens in the mitochondria as well. So this is where iron is actually added to this protoporphyrin 9 molecule. And this is when you actually have fully fledged heme. And again, because we're using a metal, or we're using a metal ion in this reaction can actually be inhibited by lead again. So lead can inhibit this reaction as well as the ALA dehydrase reaction. So just remember that, guys. Lead can inhibit both the second step of the pathway as well as the last step of the pathway. It can inhibit both ALA dehydrase and inhibit ferrochelatase, leading to anemia. And that's why lead leads to anemia. So I know this is a lot of big words. You might find that it's not easy to remember all of this, but all I would suggest is that you guys remember a few of the enzymes. And I would suggest you remember the first enzyme because that's the rate-limiting enzyme, the ALA synthase. I'd also suggest remembering ALA dehydrase because that's where lead actually acts, and that's the second step of the pathway. And I'd also say you should remember ferrochelatase, the last enzyme of the pathway, because this is also where lead is an inhibitor. So those are the three big key enzymes that I want you guys to remember. And an easy way to remember the named or the steps of the pathway, I kind of always think of something called APUC-PP. And now it's a funny way of remembering it, but the A can stand for aminolevulinic acid. The P can stand for porphobilinogen. The U can stand for a uroporphyrinogen 1. The other U, uroporphyrinogen 3. The C for coproporphyrinogen 3. The P, protoporphyrinogen 9. And then the other P, protoporphyrin. And the last one, of course, is heme. So that might help you guys out. I would just suggest going through this a couple times to get it fuller understanding of this pathway. Anyways, guys, I hope that helped. Thank you so much for watching, and have a great day.